Hi guys. Today we are gonna present our FEM Finite Element Method project. We are Yusuf Safa Ospaland and Melih Seçkin. The instructor is Farzin Mozafari. Let's start with our contents in the video. So we will first start with the problem description and we will show our analytical MATLAB solution with using the weak form Galerkin methods along partitioning methods. So after we will do same analysis in the commercial software Ansys, and finally we will compare our results. So first, let's start with our problem, two-dimensional beam truss elements. So in that figure, as seen, the truss is fixed at node 1, which means its x and y movement is restricted. Also, we have roller at node 9, so we are free to in x direction and we are restricted in y direction. So these are the parameters that given for horizontal members, Young modulus, and cross-sectional area, and these values also is given for diagonal members. So also the forces are given for at node 3 we have 5 kilonewton, at node 7 we have 10 kilonewton, and at node 4 we have 7 kilonewton, and finally we have 15 kilonewton at node 2. So in the problem, it's asked to be find the nodal displacements and reaction forces at supports, also the stresses in the truss members. So I would like to also add that all nodes are numbered and also all elements are numbered in the problem. So as seen from the figure, we have 9 nodes and we have 15 elements. So let's continue with the MATLAB solution. In the MATLAB solution, we will create first the extended node list matrix in the MATLAB solution, and I will explain this part in MATLAB. Let me show this MATLAB code. So let's start with the declaration of reaction and reaction forces and displacements as symbolic variables. So we will clarify the reaction forces and displacement in extended node lists as a symbol first, and then we will find the numerical value. So before start solving the problem, we will clarify our variables that's given. As I said, there's 9 number of nodes and 2 problem. So our problem dimension is 2, and we initialize our degree of constraint and degree of freedoms. We also initialize our extended node list as cell because we have symbolic variables. So after initialize all of these, we create node list So what's node list? What actually the node list is the position of the nodes. Uh, so let me show this. So the at node 1, this is our datum point. The x and y direction coordinates is 0 to 0 at node 1. So we enter our coordinate value according to this point. What's that mean? So, for example, at node 1, the x coordinate and y coordinate is 0. At node 2, let me show. At node 2, the y direction, the y coordinate is 2, and the x coordinate is 1. So let's see. So we declare our coordinates in the node list for each node. There are 9 nodes. After that, we enter all the Young modulus and the cross-sectional area values for each element. Like we have 15 elements, which is horizontal and diagonal. So we start with the element 1 and continue with the element 2, 3, 4, and finally element 15. And also we give the value of elements, which is 15. After that, we clarified our element list. Also, it's called the element connectivity matrix. So what is this? So this is basically shows that like first, like first element for first element, it is between node 1 and node 2. It's between node 1 and node 2. Like second element, for second element, it is between node 1 and node 3, like shown in here. So we do this logic for all these elements. And then to populate our extended node list, we create a for loop. This first for loop shows our number of rows, and second for loop shows our columns, which we have two because we have two-dimensional problem. So we have our node list as we enter. So we should implement this into extended node list as shown in this. Like first two columns is for node list, and the next two columns is for boundary condition information, and next two is for temporary degree of freedoms, and then global degree of freedoms, finally displacement and force columns. So these all things consist of two columns, because as I mentioned, this is two-dimension problem. So after creating this one, we continue with the boundary condition information. As seen from the problem, this is fixed support. That means we are restricted in x and y direction. So that means we should implement this with -1, which is directly boundary conditions. The directly boundary conditions basically means that this node is able to move in X and Y direction, but because it's two-dimensional problem. However, the Dirichlet boundary condition clarifies that it cannot move in X and Y direction if it is equal to -1. Also, we have Neumann boundary condition. Neumann boundary condition basically clarify that it can move in X or Y direction if it is equal to 1. So the restrictions are given in the problem. So for that reason, we directly give -1 to our direct boundary conditions. So let's look. This shows the number of nodes. So like for first node, we have no any movement in X and Y direction. So as you know, the first two column was for the node list, and the next two column, which is 3 and 4, third and fourth column, is for boundary condition. The third column is for X direction, and the fourth column is for Y direction. So we enter this directly boundary condition for these nodes. After that, after clarifying the directly boundary condition, we should also clarify the Neumann boundary condition. For this, we create the two for loop, which this indicates the rows, this indicates the column. Also, we add if condition. If this row and column is not equal to -1, that means it is Neumann boundary condition. Also, that means it is 3 degree of freedom. After applying all these boundary conditions, we continue with the temporary degree of freedom. In that logic, we basically clarify our number of degree of constraint in minus and number of degree of freedoms in plus. So as seen, as always, these are rows and columns. If these rows and these columns is equal to -1, that means degree of constraints. So we add -1 to degree of constraint. Else, that means if it is equal to 1, it is free to move. So we add degree of freedoms to 1. After doing all of this, we create until this, and we have these extended node list, these 6 columns. So next we will move with the global degree of freedoms. So for finding this, we are looking into temporary degree of freedoms, So if it is equal, if it is less than 0, we are adding to degree of freedoms to this number. Else, we are uh, we are just writing to same number. So after doing all of these, we have this extended node list until displacements. So as seen, these all are same because these are Neumann boundary condition. We are adding the Dirichlet boundary condition to degree of freedoms as final numbers 16. So finally, to complete our extended node list, we are creating our displacement and reaction forces. So as we did before, these are rows and columns that to clarify our inputs. So we will check our boundary condition informations. So if it's equal to -1, that means there is no any displacement in that direction. So we just enter 0 to that column and that row. So, and if the displacement is equal to 0, that means we have a reaction force at that direction, at that node. For that reason, we are giving a symbolic variable to that rows and column, like shown in that row and column. So as seen, the displacements are 0. That means we have reaction forces. Also, in the else condition, if it's equal to 1, that means we have no force, we have no reaction force, we have displacement at that node, in that directions. So after doing all of this, we have created our completed extended node list. So let's continue with the our creating our global stiffness matrix. For that, actually, uh, for that, first we initialize our global stiffness matrix. Actually, to assemble a global stiffness matrix, we are gonna use the local stiffness matrix. To find this local stiffness matrix, we just create a for loop until the 1 to number of elements. So we are getting the node numbers for each element from the elements connectivity matrix. For these nodes, for that element actually, we are getting cross-sectional area and elastic modulus values. And then after finding which nodes that connected elements have, we are getting x and y coordinate of these nodes. Actually, we are getting these coordinates to find the length of elements and also direction, cosines, and sines. Sine. Yeah. After that, we are creating the local element stiffness matrix with this formula. So also we can show this equation in that form that we get the x coordinates and the y coordinate for first node and second node. With the help of the hypotenuse formula, we can find the length, and also we can find the cosine and sine of these displacements, these x and y coordinates actually. And also there's these special formulas for the local stiffness matrix. In that formula, we use the angle between the x coordinates and the elements, and also cross-sectional area, Young modulus of elements, and also its length. So after finding this local stiffness matrix, we are assemble it the global stiffness matrix with using this special codes. So in that code, actually, we clarify our global stiffness matrix as number of nodes multiplied by problem dimension to number of nodes multiplied by problem dimension. For this for this problem, the global stiffness matrix dimension will be 18 by 18, since the 9 multiplied by 2. So after we assembly all of these for each element, we create our actually global stiffness matrix. So after that, we have a partitioning method to divide the global stiffness matrix into 4 parts to calculate our force and displacement values easily. So in that, actually, I would like to show from the presentation. So in that partitioning method, we divide the global stiffness matrix into 4 regions. In that matrix, as seen, the P refers to pre-described, and U refer to unknown. So for displacement, for unknown displacement, we say this to Neumann boundary condition, and the prescribed displacement is the Dirichlet boundary condition. That means we prescribe, we apply boundary condition, and we specify a constraint to there, like we did in the fixed support at node 1. So also these are the prescribed force and unknown force. The prescribed force are the forces that that given in the question. The unknown force are the forces, the reaction forces at the Dirichlet boundary condition. So to find the unknown displacement and forces values, we use this equation. So let's continue from the MATLAB codes. So with using this partitioning method, we found our K matrices, and we initialize our prescribed forces, and we assign our values that that shows in the question, and then we initialize our predescribe displacement, and also we calculate our unknown displacement and forces with using this formula in the slides. So after this section, my friends will continue.
Okay, now that my friend has explained the weak form Galerkin method along with partitioning and assembly operator, we are in a good position to calculate the direct stress and uh, also element forces as well. So the element force part is out of the scope of our project, but I would like to show you this part as well. So uh, we have already found the total deformation, which is UU 50 by 1 vector. So using the information of this total deformation, we can easily calculate the direct stress. But before that, I'd like to note here that we should also take into account the components of the change in length, because we have a truss beam structure with slanted elements. So we also need to take the projection of the x and y displacement. So basically, for the stress calculation, since we are in elastic region in stress strain chart, we just use this Hooke's formula, and strain is, as you know, this formula. So let's continue from coding. As you can see, we first initialized a displacement matrix, so a 9 by 2 zeros matrix. So we need to store the updated displacement using the nested for loop. And for tracking or for iterating or UU vector, we also need to initialize an index. So let me show you the total deformation vector, which is this 50 by 1 vector. As you can see, even though we should have 18 displacement values for each node in x and y direction, at total 18 values, but we excluded the restricted motion displacement in restricted motions, which is for fixed support, and the y direction of the polar support. So we are also going to include these zeros as well using this nested loop. So the logic behind this loop is like for the outer loop, we are iterating over rows, and for the inner one, we are addressing the columns. So NON is 9 and the PD is 2. PD refers to problem dimension. So starting from 2 and going all the way down to 9, we just exclude the first row of the initialized zeros matrix. So we just keep the first row as it is, because we know that at each node 1, since we have a fixed support, we don't have any motion, so we don't have any displacement. So we are starting from node 2 to ignore this node, and using this if continuous statement for the ninth row and second column, we just skip over this inner loop to have the 0 at that column. And at the end, what we obtain is, let me show you. Let me execute up till this point, and you can see the 9 by 2 displacement matrix. As you can see, the first row and the ninth row, second column, the zero values are also included. Now, using this information, we will calculate our stress values. But before that, we need to also store the zero values in a zeros matrix. We will replace these values with the updated ones after the calculations. You can see this for loop from 1 to 9, 1 to 15. You can see these are all for to have the coordinates of the elements. So we just take them from the extended node lists, and using this formula, we calculate the change in length. So this is the axial deformation. Also using this total deformation information, and we basically use this formula we also that I also told you in the slide, and we calculated our element forces and our strain as well, and ultimately we have our stress values at the end of this for loop, and the rest is nothing but the counter generation to show the deformed and undeformed truss beam overlaid in a figure. So I don't want to explain this part, so I don't want to spare time to explain this part because I'd like to keep the video shorter. So just I will scroll down slowly so that you can review this part later. Okay, that's all for coding part. Now let's move on to the setup of simulation in Ansys. So as you can see, we have our truss beam geometry designed in space claim. We designed the beam elements, 15 beam elements. So this visualization is for representing the change in the cross-sectional area for the inner and outer elements, which is also given in the question. So we assigned an edge sizing mesh with a number of division of 30 to better capture the accurate results, also at the intermediate regions, you can see. But what is different in our finite elements codes is that we didn't include the intermediate regions. What we did is assigning nodes for each intersection point. So we have 9 nodes. So we didn't cover the intermediate points. So the problem is discretized much more than that of the finite element code in Ansys. So this part is for boundary condition assignments. You can see we assign the fixed support for node 1 and the displacement boundary condition to prevent the motion in Y and Z direction for the roller support. Also, for the entire truss beam, we use the same displacement boundary condition to again avoid the motion in Z direction, but we kept the X and Y motion free. So these are the forces that we need to assign as given in the problem. And you can see we also utilize the beam tool to have the direct stress and also the total deformation. Now let me show you the deformation tendency. So you can see the undeformed structure and the deformed structure overlaid. You can see the tendency. Also, these are the force reactions you can see. Now, let me show you the comparison of the analytical and numerical results. For the reaction forces, the errors are minimal as expected because we are focusing on nodal-wise force reaction forces. So for the stress part, you can see minimum and maximum stress for both type. Also, the resemblance of the contours in MATLAB and Ansys is also obvious. This holds true for the total deformation as well. You can see how similar they are. Also the minimum and maximum results. This is the tabulation of the errors. The errors for the total deformation and direct stress are a bit more pronounced. In other words, we have a little bit more error than the reaction forces. So this could be because of the discretization type, because for the finite element method, we just deal with the nodes, not the intermediate points, but for the Ansys, you can see we have also the intermediate results. So you can see how the total deformation change along the elements. But in MATLAB, we just have these values at each node. So the error may arise because of this fact. And also, I'd like to show you the element forces as well. So let me select this axial force option and re-evaluate the solution. You can see the deformation, sorry, the axial force for each element. So also in MATLAB, what we found for element forces are as you can see these values. So in Ansys, so if we hover or mouse using our probe, we can see for the first element, you can see how similar the results are. But some of them are literally the same. So some of them are virtually the same. So for the element 3, we can see these results. And for element 4 in MATLAB and for element 4 in Ansys. So, okay, also I'd like to, also I wanted to show the element forces. So the difference between the finite element codes or finite element code and the Ansys. Okay, that's all for our presentation. So thank you for listening to us.